Well, thank you very much. Before I start, well, first of all, thanks a lot for the organizers for the great conference. I think I've enjoyed it quite a lot. And also, before I start, I wanted to give you pictures of a lot of the people who have done a lot of the work that I'm going to be talking about. So left and right, you have Carlos Garcia and Nick Cucufilipas. They're both at Oxford. Caroline Gwendolyn from Sao Paulo, who's moving now to Queen Mary University as a postdoc. Andrina Nicola at the bottom, she's a postdoc at Princeton who's just got faculty at the University of Washington. Emilio Bellini, who some of you probably know, in Geneva, and Anges Lozar in Brookhaven National Lab. All right, so I'm going to be talking first about projected large-scale structure tracers, which is a lot of this is actually something that both Stefano, Elizabeth, and also Stefan have gone through. So that's great because I don't have to spend too much time on this. But essentially, I'm going to be talking about things that are basically maps on the sky, which correspond to some radial projection of a three-dimensional quantity. So that you have the small u and the capital U are basically the two-dimensional and the three-dimensional versions of a given quantity, and we're going to be looking at several versions of that. And then, the thing that links the both of them is some radial kernel W. You can find many of these types of tracers in a photometric survey. Again, this is something that Elizabeth covered extensively, so I'm not going to go through it very much. Essentially, in a photometric survey, you don't get a redshift for your galaxies. You get an estimate of what the redshift is, but it's a very inaccurate one. So usually what you do is you try to bunch up galaxies into bins, or samples of galaxies that lie close enough in redshift that you can maybe slice them up. But you always have uncertainties on what the redshifts actually are. So the one example of that is the Rubin Observatory, which again Elizabeth covered extensively, and there's two probes there directly related to projected tracers that I'm going to be talking about: weak lensing, cosmic shear, and galaxy clustering. Again, both Stefano and Elizabeth and Stefan went through this, so I'm not going to cover it extensively. Galaxy clustering, we just look at the overdensity of galaxies and try to connect that with the overdensity of matter, and there's always uncertainties in how that relationship works, but we have reasonable models for it in terms of galaxy bias. The main thing I want to emphasize about galaxy clustering for now is that it's a local tracer of the dark matter, meaning that the radial kernel with which it's associated is the redshift distribution of the galaxies themselves. So that means if you're looking at the overdensity of galaxies at the given redshift, you're probing the same matter fluctuations at those redshifts, basically. And it might be that you don't know exactly what the redshifts are, but at least you know that whatever you're measuring is kind of local in that neighborhood of redshifts. And this will be important later. The other one is cosmic shear. Again, weak lensing, covered extensively by these guys. The main thing I want to mention about weak lensing is that, as opposed to galaxy clustering, is a line of sight integrated observable, right? So if you're looking at the cosmic shear signal of galaxies at the given redshift, you're actually sensitive not to the matter distribution at that redshift, but at all of the intervening ones. So this is an example, right? So the radial kernel at the top for lensing, it's this Q function called the lensing kernel. Let me see if I can move myself so I can see the equation. Okay. And so if you have, which is some integral over the redshift distribution. So if you have galaxies, let's say at redshift 4, you're actually sensitive to the whole projected distribution from redshift 4 to redshift 0 with some kernel. So that's galaxy clustering, cosmic shear. As they've said before, the cosmic shear is a direct tracer of matter, so you don't have to worry about galaxy bias. So this turns out to be very beneficial because when you combine both galaxy clustering and weak lensing, you can actually complement both things very well. Not only because one is local and the other one is integrated along the line of sight, but also because of how they probe the matter power spectrum. Galaxy clustering is not able to give you a good measurement of the overall amplitude of the matter power spectrum because of the degeneracy with galaxy bias, but weak lensing can. because weak lensing is projected, it basically loses a lot of the scale dependence in the matter power spectrum, but galaxy clustering can recover that. And then on small scales, galaxy bias is again very complicated, so it's hard to get very good constraints on small scales from galaxy clustering. But modeling the matter power spectrum is easier, so you can dig deeper into those scales with lensing in principle. And so combining these two is what's called the 3x2 point analysis, and I'm going to mention that later on. But again, this is something that Elizabeth covered. Okay, other types of projected tracers, for example, are CMB secondary anisotropies. So this is stuff that happens to the CMB photons as they move through the intergalactic medium. It might be that they interact with the intergalactic gas, and that leads to the thermo-Sunyaev-Seldovich and the kinematic Sunyaev-Seldovich effects, which probe essentially the pressure and the density and velocity of gas. And they also get lensed, which probes directly the matter density. So you know, through their radial kernels, we can learn a lot about the distribution of gas in the universe and its thermodynamic properties, as well as again using CMB lensing as an extra mass sheet at very high redshifts that basically will correlate with anything. Cool. And the last thing I want to mention is radio observations. So this is any kind of tracer of the large scale structure that we can come up with using radio data. The annoying thing is, if you look at the spectrum of radio galaxies, it's actually very boring. So it's mostly a power law due to synchrotron and maybe some free emission. There's very few lines. One of them is the H1 line, the 21 centimeter line, but it's quite faint. So you have several options. The first one is you can say, I really want to measure the H1 line, so I'll just spend a lot of time just looking at a few galaxies and resolve the H1 line and get a very good redshift for those galaxies. And that's fine. You get an H1 survey out of that, and you get spectroscopic redshifts, but it's usually they're usually very shallow catalogs, because you can't do this for galaxies that are very far away. The other option is say, okay, I'm going to completely forget about redshift, and I'm just going to integrate all the radio emission that I get from these from these galaxies throughout the whole spectrum, because you don't lose anything by integrating all of those, because there's no other redshift information essentially. That's what we call a continuum survey. You can go super deep with these surveys because you're integrating so much light, and also because radio emission doesn't suffer from dust extinction, so it's transparent to the galaxy pretty much. But the problem is that you have no redshift whatsoever, and that's basically like having a photometric redshift survey where you don't even have photometric redshifts. So you just have angular positions and some guess of where these galaxies might be. But they can be quite powerful for cosmology for different reasons. So it's interesting to consider them, and I'll hopefully have time at the end to get back to these. The other option is not to integrate in frequency, but instead integrate in angles. So you say, I'm going to forget about trying to resolve individual galaxies. What I'll do is I'll just point my radio telescope at a given region in the sky. I'll integrate all of the emission that comes from all the sources in that region, and that way I'll build enough signal to noise to resolve the 21 centimeter line for all these galaxies. And that's what's called intensity mapping. There's two main drawbacks from this. The first one is not so important, is the fact that you're losing angular resolution by doing this. But usually that means that you can just concentrate on the scales that we care about in cosmology, so anything larger than a megaparsec essentially. But the big problem is however, foregrounds. So just to give you an idea, this is from some simulations. This is the difference. So if you were looking at a given direction in the sky as a function of frequency, this is roughly all the components that you would see. The main one is galactic synchrotron, and that's the blue dashed line at the top. And then about 4 orders of magnitude below that, you have the cosmological signal in black, which looks like a wiggly line. And it's wiggly because it's tracing the large scale structure along that line of sight. So it's tracing all the overdensity of H1. But there's 4 orders of magnitude between them. So what you're actually going to measure is the sum of all these lines, and you need to disentangle the black line from the other ones. The good thing is that the black line is very wiggly, whereas the other ones are not. So you can use the spectral smoothness of foregrounds in order to separate them from the 21 centimeter signal. The price you pay is that you're going to be removing a lot of the smooth stuff. So smooth stuff basically means things that have you know, if you look at the Fourier transform, things that live in the low k parallel direction, basically. So you only keep the things that live in the high k parallel direction. So if we look at the kind of k parallel in the y-axis, k perpendicular in the x-axis, the blue stuff is what you have access to with intensity mapping, and all the stuff at low k parallel is forbidden by foregrounds, because you've lost all of that by removing those foregrounds. Okay, so those are the kinds of tracers I'm going to be talking about, and we are going to talk about cross correlations between all of those. Stefan already mentioned what power spectra are, so I don't need to tell you what power spectra are. So thank you very much, Stefan, again. Since Costas brought this up, I made this extra slide just to publicize a code that we have that can solve the problem of how you calculate actually a power spectrum in a realistic scenario where you have a mask and you have maybe contamination, and you also want to compute the uncertainties of those power spectra, and maybe your mask is very, very complicated, which is the case, for example, in cosmic shear. So there's this code out called Namaster that can do that for you. So just wanted to bring that up. All right, so I'm going to talk about, well, I wanted to talk about 3 ways in which we can use cross correlations for different science cases. After counting my slides, I've realized I probably have too many of them. So I think I'm going to be able to tell you about the first 2, and then we can maybe talk about the last one in the discussion session. So the first case is what I call, I think lots of people call tomographic reconstruction. So to give you an idea what this is, let's imagine that you have some quantity, some projected tracer x, which is related to some mean quantity x bar, and it traces the matter fluctuations. So it fluctuates, and this delta x traces the matter fluctuations. And imagine that you want to learn about this mean quantity x bar. If you look at the cross correlation of this map of the sky with a set of galaxies that live a specific set of redshifts, then the cross correlation is going to be proportional to the bias of your tracer times the mean value of these of the quantity that you want to recover. And so then you can do that for galaxies living in different redshifts. That gives you a measurement of this mean quantity, bias weighted mean quantity at different redshifts, and then you can reconstruct that. So I'm going to look at 2 applications of this same idea. The first one has to do with the thermal Selldovich effect. So again, the thermal SZ is a direct tracer of the gas pressure, and because things that are very massive usually have very high temperatures and pressures, it's a good proxy for cluster mass, basically. So you can use it essentially. You can use maps of the TSZ Compton Y parameter, which is this Y quantity here, in order to locate clusters of galaxies in a CMB map. You can then try to do cosmology with those clusters, and this is, for example, some constraints from Planck from back in 2015. So there's been, you know, updated versions of this analysis, but back then one of the problems was that if you tried to constrain sigma 8 and omega m, you got something that was in somewhat in tension with the Planck primary CMB constraints in black, very similar to what the weak lensing analysis are getting, which I'll get back to later. Of course, when you do this, the main problem is the uncertainties that you have in how you link this Compton Y parameter with the actual mass of your cluster, which is the thing that you can use. And so there's uncertainties in the Y-M relation. These are usually phrased in terms of something called the hydrostatic mass bias, this 1 minus m, which is related to how X-ray masses are measured, which are very often used to calibrate these kinds of observations. So essentially, 1 minus b is how much mass you're missing when you try to infer the mass of a cluster from X-ray observations, which is a kind of contrived quantity, but that's basically what it is. And what you can show is that in order to make cluster SZ cluster observations from Planck agree with CMB primary data, then you need to make this quantity 1 minus b be about 0.65 or something like that. So basically, you lose about 35% of all the mass when you look at X-ray data. Hydrodynamical simulations don't support that. The idea is that it should be more like 80% or above, and weak lensing cross-calibrations, they prefer something in between, probably. So one thing you could do is you could take this concept of tomographic reconstruction to try to constrain the evolution of this quantity as a function of redshift and see whether or not, for example, assuming that it's a constant quantity is a good thing to do, or whether it does something weird. More generally, what we can do is we can try to constrain the evolution in the mean gas pressure as a function of redshift. So this is something that Nick Cucu-Filipas did, picture there at the bottom. He cross-correlated the TSZ map from Planck with data in 6 redshift bins from the 2MPZ and WISC WISE cross supercosmos catalog. So these are 2 photometric redshift surveys at very low redshifts, but really, really dense. So you have lots of galaxies with not so good redshifts. He measured the power spectra. You can see here some of the power spectra with the autocorrelations of the galaxies and the cross correlations with TSZ. So the autocorrelation is going to be proportional to the bias of the galaxies squared. The cross correlation is going to be proportional to the bias of the galaxies times some power of 1 minus b, or in other words, the bias of the galaxies times the bias weighted mean pressure. So by combining both of them, you can measure then the bias weighted mean pressure or the hydrostatic bias. So you combine both of them, you get a measurement, and this is the result that Nick got. Forget about the first point because the uncertainties there are really huge, so they're compatible essentially with everything. The 2 main conclusions is that there's no evidence of any kind of redshift evolution for this hydrostatic bias, and also that the measurements that you get through this cross correlation are actually in good agreement with, for example, the type of constraints that you would expect from hydrodynamical simulations, more than what you would need in order to make CMB primary data compatible with CMB cluster data, sorry, with SZ cluster data, which is the gray band at the bottom. So that's interesting, and Nick is currently following this up with a combined analysis where he brings in also CMB lensing. So that's a paper that's in preparation. To me, more important than this kind of contrived quantity, which is the hydrostatic bias connected indirectly with X-ray data, the cool thing is that you can actually measure the evolution of gas pressure as a function of time, and that's what's shown here. So the Nick's measurement are the purple or blue points, which are the most precise ones to date. So compare that, for example, with the DES measurements. And the key here is that we're using catalogs that have a really high density of galaxies. And they agree fairly well with halo models, halo model predictions for this mean pressure. Right. Can I check that you guys are hearing me?
David?
Yes.
Can you hear me?
Yeah.
Just a quick question. Sorry,
yeah.
I must have missed it. You showed that the hydrostatic bias didn't look. I mean, doesn't look like it changes over redshift, right? Yeah.
Yeah.
But the bias weighted mean pressure does.
Mm-hmm.
But then aren't they not like the same thing roughly that you were showing?
They're not, right? So
so if you go to the previous slide, or maybe okay,
right. So the proportionality constants are not the same for the two lines, right? So in one there's a redshift dependent quantity that depends on the
it's in there, it's in the okay, thanks. Sorry,
exactly. It depends on halo bias and on the mass function essentially, and how that changes with redshift basically.
Okay, thanks.
Yeah. Cool. Okay. I was freaking out because I wasn't sure if you guys were still hearing me. So that's really great. Thanks. All right. So this is one example of tomographic reconstruction. I'm gonna talk about another one, which is related to this S8 conundrum, but I think was touched upon by Elizabeth. So there's, in 3 times 2 point analysis, the main quantity that gets measured is this combination of sigma 8 and omega n called S8, which you can see at the bottom of the right hand plot. And what I've plotted there on the left, you have a plot from a kid's paper with their measurement and a couple other measurements. You can see a compilation of the latest measurements of this quantity on the right hand side from different types of data sets. And this is actually out of date. There's even newer measurements, but the conclusion is always the same, is that these measurements seem to always be lower than Planck. Individually, they're not at more than 2 points a little bit sigma, but the fact that there's many of them makes you scratch your head. So one of the things we wanted to do was to try to use this idea of tomographic reconstruction to try to understand exactly what's going on with this disagreement. And so here's the idea. In principle, cosmic shear already gives you a measurement of sigma 8, but what we can do when we cross-correlate with galaxy clustering is to slice up sigma 8 as a function of redshift, essentially, and essentially look at the linear growth factor as a function of redshift and see where it departs from the lambda CDM prediction, for example, from Planck. So this is something that was done led by Carlos Garcia and others at Oxford. So the goal is, as I said, is reconstructing the growth history by using as many data as we could, because we were going to use all this data and figure out a way to combine all of them. We could almost for free also get associated constraints from the combination of these data sets. So I'll show those as well. So I'm not going to go through the details of the analysis. That's all in the paper. There's really cool stuff on how you combine all these data sets, making use of robust ways of computing covariances and things like that. But I'm not going to bore you with that. I'm going to just show off how many data sets we put together. So these are DES and KITS, but also galaxies from the DESI legacy survey. So galaxy clustering from that, EBOS quasars, and CMB lensing from Planck. So it's 6 different data sets that were put together. And you can see the redshift distributions there, which allow us to basically track the evolution of the growth of structure from redshift about 2. Right, so this is the measurement. So on the right hand side, you have basically sigma 8 as a function of redshift scaled by omega m, because that makes our error bars look smaller, because that's the direction that breaks the degeneracy in the final constraints. In blue, you have the prediction from Planck, including the error bars of Planck, and then in red you have our predictions or our results if you put together all these data sets. All the other bands are basically breaking up the data sets into different subsets. Either we only look at things in the south, which is DES, or things in the north, which is KITS and decals. Or we...
David?
Yep.
Hi, I'm Diego. Sorry, I got a bit lost. So what is the thing that you are varying over redshift, and which is the one that is... So what are you really cross-correlating with what?
Right, so...
in this particular...
Yeah, so I went a bit too fast over this, right? So we have 3 types of data sets here. We have cosmic shear, which is just weak lensing at different redshifts. We have CMB lensing, which is weak lensing at redshift 1000. We have galaxy clustering from DES and the DESI legacy survey, DELS, I'm calling it here, which are the basically measurements at redshifts lower than 1, which you can see at the lower end. And galaxy, so quasar clustering from EBOS, which gives us a handle at higher redshifts. And we're looking at all the autos and cross correlations between all these data sets.
Okay.
Yeah.
So basically, in this plot is a kind of static view of what you were showing before, changing different redshift bins.
Yeah. So
like
you can
these peaks and the foreground, let's say, signal, and you kind of cross correlate all possible combinations.
Exactly. So think of CMB lensing and cosmic shear serving as a background map of the matter distribution, and then you're slicing that up with all the galaxy clustering data sets, essentially, and making a tomographic measurement like this of sigma 8, essentially. Yeah. Okay. Right. So I was going through this. We look at different slices of the data. Let me just give you the main results. Right. So what we can see is that the main source of the disagreement is galaxies that live at around redshifts between 0.2 and 0.6. This is natural because this is actually the range of the range of redshifts where we have the most data or where we have the most constraining power from both cosmic shear and galaxy clustering. We need better data at higher redshifts in order to make a better measurement of this growth evolution. Both DES and KITS, which we call north and south, essentially, they give very compatible results in this sense. So which is good, because that means that this is not coming from systematics in one or the other. Probably it might come from systematics in how things are being analyzed in both of them, for example. But the tensions does seem to be driven by shear data, at least in these data sets. There's other people who have measured this without shear, and they also get some kind of tension, but we don't. Yeah, and so if we remove shear from our analysis and we keep only galaxy clustering and CMB lensing, it's things are compatible with Planck, but they're also compatible with shear because the error bars are larger, basically. And then, as I said, we will need better data at higher redshifts in order to make this story complete at higher redshifts and actually trace the growth structure more precisely. But this is pretty cool. And we'll get that from Rubin, Euclid, etc., etc. Because we could get also constraints on S8 directly without breaking the growth structure up into different redshifts. We did that, and so these are the constraints that Carlos got in red. They're the tightest so far until you look at the archive in a couple of days, probably. And you know, the level of disagreement is at I think I wrote 3.5 is actually 3.4 or something like that. But you know, things are getting to the point where you need to start wondering whether there's either new physics or it could be just some systematic that we're missing in how we analyze the cosmic shear data. Good. Okay. I'm not sure how much more time I have, but hopefully I can talk about at least part 2 of the talk.
15 questions.
Okay. All right. Interrupt me whenever you guys want. Hopefully I'll get to the end of this part, and then we can break. All right. So the second part is calibrating redshift distributions, which seems like a very boring topic, but it turns out to be relatively fun. And the idea is very similar to tomographic reconstruction, actually, but I separated it because it's I would say less directly science related, but indirectly is very important. So okay, so in a photometric redshift survey, we said we don't have good redshifts. We slice galaxies up into samples of galaxies that we think live at the same redshifts, but we're always going to have some uncertainty over what the distribution of those redshifts actually is. So these are redshift distributions coming from the HSC data, and these are actually estimates of the redshift distribution. We don't have a complete certainty of what the redshift distribution actually is. So how do we usually do this? The canonical idea is to say, okay, I have my photometric sample for which I know colors. I don't have spectra, but I have colors of this photometric sample, and it lives in this region. I may have specific parts or specific regions where I've actually conducted a spectroscopic survey and I've measured spectra for some of these galaxies. So then you could say, well, that's it. You just need a subset of redshifts, you map them out, and then you have a redshift distribution. But the problem is that the spectroscopic sample usually looks like this. It doesn't really trace the same color distribution as the photometric sample. So you will be missing redshifts for classes of galaxies that you actually have in your data if you do this, and that's often what happens. So something you can do is maybe you can reweight your spectroscopic sample so that it matches the photometric sample. You weight more some galaxies than others, and maybe you can try to map the same color space, but it gets tricky. Because that's not always possible. If you have 0 galaxies in a given region of color space, then 0 spectroscopic galaxies in the region of color space, then you're in trouble. So there's always uncertainties on the final redshift distributions. One typical way of accounting for those is basically giving them a nuisance parameter. So let's say we don't know, we have an inkling of what the shape of the redshift distribution is, but we don't know exactly what the mean is. So we're going to marginalize over that with some prior. Or we could marginalize also over the width of the distribution. So that's the one option, which is probably the best we can do with the data very often. Another thing that is interesting is that you could even try to use your own data to kind of self-calibrate some of these uncertainties, and this is something that Andrina showed in this analysis of the HSC data. So very often you discard cross correlations between different galaxy clustering redshift bins because they are very sensitive to uncertainties in the redshift distribution, because they are very sensitive to the overlap between different redshift distributions. But you can turn that around and say that those cross correlations actually help you calibrate what the redshift distributions actually are. And one of the things that Andrina showed in this paper, which is actually one of the tiny things that she showed, the paper contains a lot of cool stuff. But one of them is that you can actually constrain the relative separation between redshift bins by looking at these cross correlations. So you shouldn't be throwing away these cross correlations, because they actually contain important information about the redshift distributions, which at the end you want to calibrate anyway, because otherwise your weak lensing data will be wrong. There's forecasts from Manu Shan in this other paper that I'm linking at the bottom, where he takes this to the idealistic level, where we say, okay, let's combine actually all the data, not just cross correlations between clustering bins or whatever. Let's imagine that we use all the data in the Rubin Observatory, for example, and we see to what extent we can actually self-calibrate these photometric redshift uncertainties. And the answer is that in principle you could do a pretty good job at it. There's always challenges, but this idea of self-calibration is not too bad. So that's fine. If you want to make extra share of the fact that you have the right redshifts, which is always a good idea to do, there's another possibility, which is what people call cross correlations redshifts or clustering redshifts. So the idea here is basically illustrated by these two images. So on the left, let's imagine that you have a photometric redshift bin with some unknown redshift distribution, which I've plotted in red here. And you have a spectroscopic sample that overlaps with the same galaxies. And it may be that they don't represent the same galaxies in color space, but at least they overlap and they're tracing the same large-scale structure as the photometric galaxies. So you slice up your spectroscopic bins because you can, your spectroscopic sample because you can into very thin slices. You cross-correlate each of them with the photometric galaxies. And then the logic says that if you have no photometric galaxies in a given redshift, then the cross-correlation will be 0. If you have lots of them, the cross-correlation will be very high. And that's what you can see in the right panel. That basically gives you the amplitude as a function of each of the different spectroscopic redshift slices. And you can see how the amplitude of the cross-correlation traces the redshift distribution itself. So this is the idea behind cross-correlation redshifts, which is a very old one, and I think I probably should have put all the references here, and I didn't. So apologies for that. So for that, you need a spectroscopic sample that lies at the same redshifts. The advantage is that it doesn't need to cover the same color space. But a question you could ask yourself is, can we do this with 21 centimeter data? Because in principle, 21 centimeter is also something that has very good redshift resolution, so you can slice it up into small redshift bins. And the main problem there is again foreground. So just going back to the picture that I showed at the beginning, intensity mapping only lives in the high k-parallel region, and you're going to try to cross-correlate that with photometric sample, but photometric samples only live in the low k-parallel region, because photometric redshift uncertainties is basically killing all the high k-parallel wavelength modes. So if you look at the cross-correlation, let's imagine that we take the power spectrum between intensity mapping and the photometric survey. Because of statistical homogeneity, that needs to be proportional to a delta function that forces k H1 and k galaxy to be the same, but they actually live in these joint regions of k space. So you get 0 correlation, or in practice you will get a very small correlation. So that's annoying. The other possibility is you could look at higher order correlators. So you could look at bispectra. And there's two reasons why this is a good idea, or there's two ways to explain why it's a good idea. There's the mathematical one, and there's a physical one. The mathematical one is very simple. If you just use the same idea using statistical homogeneity, tells you that if you look at the bispectrum, which contains one leg of the galaxy photometric galaxy survey and 2 legs of the H1 map, that's going to be proportional to a Dirac delta that contains the sum of these 3 Ks. So you can actually have a very small K galaxy, so a small or a large wavelength in the radial direction, large wavelength mode, connected by 2 small wavelength small wavelength H1 modes, so 2 high K modes, which allows you then to escape this kind of foreground-dominated region. So this is all very mathematical. You can see how that happens physically as well, in terms of this idea between this idea called the peak background split, which tells you if you have a long wavelength density fluctuation, you could think of a region of high density as being an effective universe where the omega matter, for example, is larger, and then you would expect that clustering would be higher in that universe than in a universe with lower omega matter. So you could think of mapping, for example, the local variance of the H1 map as a function of position in space, and that local variance would correlate with the long wavelength density fluctuations, and so that will give you a bispectrum basically with 2 small wavelengths H1 modes and 1 large wavelength galaxy mode. Right. So again, this is something that was looked at by Caroline Gondalin in a paper that we put out yesterday just for this conference. I'm not going to go through the details. There's a lot of math in the paper you can do to you can go to if you want to learn more about bispectra. We actually learned a lot, but this is the main idea. So let me try to explain this plot. So on the y-axis, you have the constraints that you could get on the mean of a photometric redshift galaxy distribution. And it's expressed in terms of a moving distance instead of redshift, but just think of redshift if you want. And this is a function of the redshift of the mean redshift of this redshift slice in the x-axis. If we focus on the light band, that tells you the kind of constraints that you could put on this quantity if you were using just the power spectrum. And at the lower end of the band, you have what happens if your photometric redshift uncertainty is 0.02, or if your photometric uncertainty at the upper end is 0.05. So if your photometric uncertainty is 0.05, which is very realistic and very possible, your constraints are crap, and they're much higher than what you need to achieve for LSST, which is shown in the dashed black line. So the power spectrum doesn't allow you to do this. If you then go to the dark band, that shows you the same kind of limits for the bispectrum. And you can see that the bispectrum is a lot less sensitive to how accurate your photoseeds are, and you can always beat the LSST requirement with this. And of course, the advantage of doing this with intensity mapping is that it's easier to go to higher redshifts with intensity mapping than measuring spectra for lots of galaxies at high redshifts. So this could be particularly powerful in that regime. How much time do I have, Fede?
You are 3 minutes from now.
3 minutes. Okay. So I'll just say something else very quickly. Well, just to say that a similar idea could be applied to other actual science cases, for example, measuring FNLs from the bispectrum, which peaks at this kind of same squeeze limit. And you need, again, high redshift, large volumes. All right, so I promised I was going to talk about continuum surveys as well. So this is an example of the main problem of continuum redshift surveys. Continuum radio surveys. So you have here 3 different redshift distributions in red, green, and blue for a sample of continuum radio galaxies called the LOFAR 2-meter survey, I think, LOTS. Red is what you get if you measure photometric redshifts for a few galaxies, for which you can do this and just bin them up. Green is if you do a very deep surveying in a given region in radio and try to measure as many redshifts as possible. And then blue is what you get if from a simulation that uses some models for the luminosity function of galaxies, the radio luminosity function. And they're very, very different, and you have no idea which one is better. And the main thing that they differ on is how deep they go in redshift, so how long the tail of this redshift distribution is, so how wide the redshift distribution is. So what we did in this paper, we tried to constrain that essentially the tail of the redshift distribution, how wide they are, by looking at cross correlations with CMB lensing. So this is something that I did with Emilio Bellini and others. These are measurements of the cross correlation between the at the bottom you have the cross correlation between these LOTS galaxies and CMB lensing, and at the top you have the autocorrelation. So how can we use this to constrain the tail of the redshift distribution? You can see that both cross correlations are kind of boring. They all look like power laws, so it's not like you can constrain much from that. But let's look at this. So so there's two things that affect the amplitude of this cross correlation. One is the bias of these galaxies. So you can see here how the autocorrelation and the cross correlation depend on the galaxy bias. So one of them will depend quadratically, the other one will depend linearly, essentially. If you do the same thing but varying the tail of the redshift distribution, the autocorrelation is very, very sensitive to the tail of the redshift distribution. And that's because if you make your redshift distribution wider, it goes down in amplitude because it needs to integrate to 1, essentially. Whereas in the cross correlation, you only care about the overlap between the two things that you're cross correlating, and no matter what the width of the redshift distribution is, you will always have the same overlap with the CMB lensing kernel, which is very, very wide. Which means that you can actually break the degeneracy between these two parameters by looking at these two distributions. By looking at these two power spectra, and these are the constraints on the tail of the redshift distribution that we got, which actually agrees pretty well with the spectroscopic follow-up. You can play the same game with anything that modifies the width of a redshift distribution or of a radial kernel. So, for example, remember that the weak lensing kernel, the width of the weak lensing kernel basically depends on where your galaxies are, rather than the width of the redshift distribution of those galaxies, because it's a cumulative distribution. So in principle, by looking at cosmic shear cross-correlated with CMB lensing, you could also constrain the mean of a redshift distribution for your cosmic shear galaxies. And this is something that Naomi Robertson showed using kits and CMB lensing maps from ACT and Planck. So it's a busy plot, but basically what I circled in blue is the constraints that you can actually put on the mean of the redshift distribution for a high redshift sample, and that's because it affects the width of the lensing kernel. So anything that affects the width of a kernel, you can constrain through CMB lensing cross correlations. And I'll finish here. I'm going to skip the last part, which was about detecting new effects. I think actually Stefano covered a lot of this. So just wanted to thank you guys again for inviting me. I'm really sorry that I couldn't be there. There's lots of cool stuff about Prague that I'm missing. But then Diego showed me this picture, and maybe it's okay if I stay home. I don't know. But yeah, thanks a lot. And I'm truly sorry that I couldn't be there. Thank you.
Okay, so do we have any more questions before the break? Iggy, okay.
Hi, it's Iggy here. I just have a question about your first part. So when you were showing this evolution of S8 as a function of redshift, or sigma 8 as a function of redshift, is there, so there's this dip, which looks very suggestive, but is there is that statistically significant in any way for you? Or
yeah, so
that you could just renormalize the, let's say, sigma 8 at redshift 2 or something like this, and you basically match the lambda CDM evolution then.
Right. So so the measurements that we have are basically this one, right? So they're the intersect between, let's say, the red bands and the dashed lines, the dashed vertical lines. Those are the actual measurements that we have, right? So the ones at low redshift are the ones that are actually in tension with the CMB data. If you calculate the tension, is again at the level of 3 sigma or something like that. But you can show that this doesn't say that lambda CDM is wrong. Our measurements are actually okay with lambda CDM. It's just that you need to rescale down sigma 8 or S8 by some amount, by a little bit, which then puts you in tension with Planck. So lambda CDM is actually able to give you these measurements easily, but not with the same amplitude as Planck would prefer, basically. Yeah.
Okay, great, thanks.
Stefano.
Hi again, this is Stefano. Thanks for the talk. Amongst the many questions that I have, let's just pick up one. In the last part about the bispectrum to calibrate photometric N of sets. So if you have the two modes, I mean the two long K modes are intensity mapping. In any case, if you have two intensity mapping deltas in your bispectrum, shouldn't you worry about foregrounds? for them?
You need to worry about foregrounds from them for them, but we know that foregrounds live in sorry. No, so these are, no, you don't, right? So, sorry, you don't, because these are long wavelength modes. Sorry, they're short wavelength modes, right? These are high K
in any
modes.
case, you have to do foreground removal, but at least they won't, affect those. Yeah, okay.
So they're going to live on this, on the upper part of this plot where you're less sensitive to foreground. So these are the modes that you can actually hope to clean sufficiently well, basically. Yeah.
Okay, no, that was clear. It was just the fact that I was wondering, in any case, you have to do some foreground removal, but that shouldn't affect too much. Well, but in principle, you should also be able, you could also do 2 delta G and 1 delta H1 with some combination such that your KG isn't too large.
I don't think you can close a triangle with two small sides and one large side, right? I think that's the problem.
How small they need to be. So you could, instead of a squeeze, you could work out a flatlet triangle. Might be there's some constraining.
So if you look at the typical photo Z uncertainty, and you look at the typical scale where if you run a simulation, you see, okay, I can definitely clean foregrounds down to this, but beyond this is completely anyone's guess. They annoyingly they usually in scale. So if you look at the corresponding comoving scales, the K values are usually about 0.02 inverse megaparsecs, which is extremely annoying. So there's really, a lack of overlap between the two.
Okay, really little.
Yeah. I mean, optimistically, maybe we come up with really good foreground models and we can clean them up much better, and none of this is actually needed anyway, right? But at least if we're conservative and we look at current simulations and things like that, it looks like that essentially. Yeah.
Yeah. Okay. Thanks. Cheers.